Mark's telling us about advancements in quantum cryptography.
Yeah, thank you very much. Yeah, so I'll just jump right into it. So this morning, we're going to have a little crash course in quantum computing just to make sure we're all on the same page. Then I will discuss how quantum computing impacts existing crypto systems that are, out there today. And then for most of the morning, hopefully, we will spend on just an overview of the field, at least the field as I see it, talking about new cryptographic assumptions, new security proofs, and new definitions that are all needed for this quantum world that's hopefully coming soon. What was that? Hopefully, yes. All right, so let's dive in to quantum computing. So I'm going to start by talking about a classical model, which is just modeling uncertainty using probabilistic systems. So I'm going to imagine that we have some distribution over values, I guess, x, and we can represent this distribution by a vector, where each component of the vector corresponds to one of the possible outcomes of this distribution. So here I have this vector v, and the requirements are that all the entries are non-negative and they sum to 1. All right, so we can then act on this probability vector through a stochastic process, which is given by matrix A, and the action is just multiplying A dot B. So here A represents, if the state is in state X, then you move to Y with probability AYX. Right? And if you do this product between A and V and your initial state vector V, you will actually get the resulting state vector after applying this stochastic process. I wanted to say for the moment, I'm not paying attention to anything computational. This is just purely information theoretic. And then finally, we can get information out of this probabilistic system by just looking at it. So if we look at the system, then we know which state it's in. And so in that case, the state vector collapses to have all of its amplitude on whatever the observation x was. Right? So this is just a very simple model for classical processes. And now we'll see that when we move to quantum, we don't actually have to change a whole lot. Oh, sorry. Before I get into that, I just wanted to give another view. So we can imagine maybe we have like a particle or something going through the system. Here, the white space is going to be whatever the system is, however it's acting on the states. And these bars the gaps are going to kind of be the possible outcomes at any particular time. So as we imagine our system or this particle moving through the classical system, it's really tracing out a path. Now, we don't know what the path is because we haven't, at least until we look at the system, we don't know what the path is. It could have gone in many different ways. But we can describe the probability of observing an x at the very end by looking at the paths. So each path has a weight, which is just the product of the probabilities along that path. So right, if your path is here and it moves here, you had this transition matrix, a stochastic matrix that told you what the probability of moving from here to here is. So if you multiply all those probabilities together, you get the probability of a particular path. And then you just sum all the paths that lead to x, and that's your overall probability. Okay, so quantum systems basically are the same idea, except that the mapping between the underlying amplitudes of this vector and the probability of an observation, we square it. That's basically the only difference. So in a quantum system, the state of your system is an amplitude vector. Now, this amplitude vector can actually be positive, negative, it can even be complex number. And the requirement is that the sum of the amplitudes squared have to be 1. So rather than the sum of the amplitudes being 1, now it's the sum of the amplitudes squared being 1. Okay, and now how do we act on this? Well, we're going to still act by linear transformations, except that these linear transformations are going to be different than the ones in stochastic processes because they have to preserve the norm. All right, and it turns out that the thing that preserves the norm is something called a unitary matrix. And this is a matrix where the conjugate transpose is its inverse. So the conjugate transpose, for those of you who haven't seen anything with complex numbers before, you basically take the transpose of the matrix and you replace everything, anytime you saw an I, you replace it with minus I. Okay. I should point out that for the purpose of this talk, most of these details are gonna not be super important, but I wanna cover them anyway, just for completeness. But hopefully if I'm going fast, it's okay, because we won't actually care about unitary. All right. And then, okay, so how do we get information out of the system? Well, we do it by looking at the system. But it's gonna be a little different than the classical case because of the squaring. So now when we look at the system, we're going to get x not with probability Vx, but with probability V sub x squared. Whatever the amplitude squared is gonna be our probability. And then just like in the classical case, the state now collapses to a vector that has all of the amplitude on whatever the observation was. And you can check that by defining our probability of an outcome x in this way, it actually is a probability distribution because these Vx squareds all sum to 1. They're non-negative, they sum to 1. So if I sum up all these probabilities, I get 1, and therefore it's an actual probability distribution. Okay, and we can also look at it in this kind of path version. So the weight of a path is going to be exactly the same as it was before. It's just the probability, the product of the weights of these unitary matrices along the path. But then the probability of a particular outcome, we sum up the weights on that path just like we did before, but then we have to square it, just because we're moving from just the probabilities being the weight itself to the square. So it's the same thing except we put a little square on top. And I guess I should just give a little intuition for why this is the model of reality. And I think this picture, hopefully, with some more words, will give some intuition. So there were a lot of these tensions between in physics in the late 1800s into the early 1900s, and one of them was this wave-particle duality. So if we actually imagine like a discrete classical particle moving through a system, it would behave like the probabilistic process that we had before. But then there was this tension because it also appeared that particles behave like waves. There was the famous double slit experiment. And for waves, you can imagine these amplitudes being like the electric field or something like that. And the energy, which roughly corresponds to the probability of, the fraction of photons that you would see here, would be kind of the energy of all the light that's here. That energy is related to the underlying electric field by the square. So then you end up getting quantum mechanics when you kind of like try to force these two things together and consider individual photons that are both sort of behaving like particles and also like waves at the same time. So that was like a absurdly brief kind of overview of quantum, but I wanted to keep it brief just so we can actually get into the interesting crypto. Yes.
So, okay for this because of reality, but leaving reality aside, from a computing, no, we are theoreticians, okay. So, from a computing point of view, this seems so similar to the probabilistic description that what makes this more powerful? Oh,
next slide. Yes. Thank you for being my plant. Okay, so there are a couple conceptual differences between thinking of classical but probabilistic processes and thinking about quantum. So one is that quantum states are actually physical states. I'm not just modeling uncertainty. In kind of the language of quantum mechanics, we call them pure states. So it's actually a real state. It's not just that I don't know anything about it. And I think more importantly, it's this fact that paths can interfere. And you can have both constructive and destructive interference. So constructive interference is where the sum of the weights of the paths squared is greater than the sum of the squares of the weights of the paths, and you can also get destructive where it's less than. And in the classical setting, because in the classical probabilistic setting, you remove these squares, and so everything's linear, and so the sums just move around wherever you want them. But in quantum, you get this constructive and destructive interference. So what does that result in? So one thing is you can actually, if you have a quantum state, and you want to check whether it's the quantum state you think it is, you can actually do this. So for any supposed quantum state V, I can define a unitary UV that maps my V into, 1, 0, 0, 0, 0, and maps everything else to being far away from 1, 0, 0. And what this means is, if you know what V is supposed to be, you can construct this unitary UV, and then you can actually check if a state is the state V that you think it is. The equivalent for stochastic processes, it doesn't really make sense. So the equivalent would be given a sample from a distribution, because remember, it's just in the classical case, we're just modeling uncertainty. So you're actually given a sample from this distribution. Can you decide if that sample came from a distribution V or came from a totally different distribution? But obviously from one sample, you learn nothing about the distribution other than the samples and the support, so you can't actually do this. So the classical analog of this is not possible.
You're saying in the quantum setting it is possible?
Yes, so in the quantum setting, if I hand you a state, you don't know what it is yet, but I claim it's a particular state V, you can actually verify that the state I gave you was V.
But I'm not sure I understand, because even if you have this equation, then you will measure the top, but perhaps your measurement gives that with some probability, and you cannot sample it again, because once you measure, you cannot boost.
Yeah, I did lie a little. So yes, an arbitrary V will have probably some amplitude there, but it'll be small. And if you have a vector that's like at least far in some sense from the given vector, then the amplitude will be extremely tiny, or even 0.
So it doesn't, so you lied about the fact that it doesn't have to be exactly V?
That this test will have false positives, basically. That you can be close to the right vector and it'll still accept it, but if you're far from the right vector, then you're guaranteed to reject.
But you can boost it if you...
No, not if you're just given one copy, you can't. Yeah, but the analog for the classical probabilistic setting, basically all you can check is support. Whether, if I give you a vector, well, you know that that's at least in the support, or sorry, if I give you a sample, you at least know it's in the support of the distribution, but that gives you a lot less information than what you get. Another thing that I think is a really important concept in quantum is, imagine we do 2 measurements. We measure here, and then we measure again here. So what's going to happen? So in the classical setting, I can calculate the probability of seeing a particular value x here and a particular value y here. And it's just the sum of the weights of the paths, but I restrict the paths that go through x and then end at y. Right, very simple. And if I then say, okay, well, I did this, and now let's say I throw away x, I forget what x was, and I just ask what was the probability of observing y. Well, I do the usual thing. I take my probability of x and y, and I just sum over x. And by linearity, I get exactly the same probability of y that I had before. So observing x here didn't change the probability outcomes for y. But when we move to quantum, this is no longer true. So when we move to quantum, it's still the case that I sum over all of the paths that hit x and then y. But remember, I have to square to get the probabilities. And now if I take my probabilities of x and y, I sum over x, I get this expression here. But the original probability, the probability of y, if I just, never measured x, this probability has the square on the outside of the big sum. And so as a result, measuring this x here and looking at the state of the system at some point in time actually affects the state of the system at later points in time. And this is called the observer effect or measurement principle or something like that. But it says that in quantum mechanics, you can't just look at a system and have the system also stay in the same state. It will, no matter what you do, if you're like extracting information here, you risk changing the state at a later point in time.
The reaction, you don't know if it will go in both directions, right? It's not...
It could go in both directions, yeah. Okay, and then the last kind of difference I wanted to talk about is something called cloning. This isn't super important for this morning, but will become relevant in the afternoon. So there's this thing called the no cloning theorem in quantum mechanics, and there's actually a classical no cloning theorem. So you get no cloning just by linearity, but the classical no cloning theorem doesn't really mean much. So in the classical formulation, there's this no cloning in the following sense. If you have some unknown stochastic process or stochastic state, and I just give you a sample from that unknown distribution, can you produce two samples from that distribution? And the answer, two independent samples. And the answer is clearly no, unless you're guaranteed that the distribution, you know, is like, it only outputs one value ever. In general, given one sample from a distribution, you don't have enough information to produce a second sample. But that's not particularly interesting. And remember, we're just modeling uncertainty. These probability vectors actually aren't physical. But when we move to quantum, we get the same no cloning theorem, except that actually now it's a physical state, and now it's really actually meaningful. So it says that if I give you some unknown quantum state, you can't produce two identical copies of that unknown state. All right? And this, again, this won't be super relevant this morning, except that, you know, if you have this in your mind, some things, some strategies that I'm saying aren't possible, they aren't possible because of this no cloning theorem. In the afternoon, you'll see how stuff like no cloning and just kind of these features of quantum actually leads to interesting quantum protocols, but we're not going to concern ourselves with that for now. Okay, and then what is quantum computing? Basically, I think you know, there's many different ways to think about quantum computing. Some are maybe a little inaccurate, but here I think this one is a not inaccurate way of thinking about quantum computing, is that you're really taking advantage of constructive interference to get the right answer with higher probability than you would classic. So you imagine your quantum computer is now running this quantum process, you're trying to, you're gonna do a final measurement to get your outcome, and you're hoping that you can constructively interfere all these different paths to get a much higher probability of the right outcome than you could classically, where you don't get this constructive interference. And if you can get it with higher probability, maybe that means you can need fewer steps and you can therefore get your answer faster. All right. So I'm going to introduce a bit of notation. I'm going to try to keep the notation light, but it's a little unavoidable, I think. In quantum, we like to use this ket notation, where just if you see you know, vertical line in this angle, that just means that's a quantum state, a pure quantum state. And we have these special ones that where if we just label them with a classical state 0, 1, 2, whatever, these correspond to just all the amplitudes on 0, all the amplitudes on 1, etc. And then we can define kind of a general vector as a linear combination of these basis vectors. Okay. So first thing, I guess, about quantum is that quantum actually is better than classical. We can do more. I won't prove this, but if I have a classical function f given as a circuit, I can map it efficiently. Oh, and I haven't actually defined what it means to be an efficient quantum circuit. That's not going to be really relevant for this morning, but just, you know, there's an analog of the classical circuit model for quantum, and we're just going to take that for granted. And if I have a classical circuit of some size, I can map that with polynomial overhead to a quantum unitary that performs this operation. Basically, it takes x and y and maps it to x, comma, y, x, or f of x. So effectively, it's computing f of x, because you could initialize the y to just be 0. And you might ask, why is it this form? Why aren't I just outputting f of x? And the thing is that unitary operations are reversible. So if I didn't have the y's here and I just, you know, mapped x to f of x, this wouldn't even be a valid quantum operation if I didn't do something like this. And also, in order to actually make, even if f is like a permutation, in order to make this transformation efficient for general permutations, you know, we still need to do something like this. So even if it's a permutation, it's not necessarily true that we can kind of efficiently map x to f of x in place. We always have to write it to another register. All right, so, but this is enough. Like, if you want to compute some classical function f on any input, you just initialize the system to that input, comma 0, apply the unitary, and you'll get what you want. Okay, and now there's there are things that quantum computers can do that classical computers can't do. And I'll tell you about the quantum Fourier transform, which is kind of the main tool that we use. There are others, but this is the main one. So for those of you who have seen some signal processing stuff, this will look familiar. But if you have not, you'll just it's just a formula. So if I have some state that's a superposition, over some arbitrary quantum state with these amplitudes, and remember these x's are these 0, 1, 2, whatever. I can map it to a different state that I'll denote with the hats with these transformations here. So if my alpha vec, if I have certain alpha x's on the left, they'll map to these alpha hat y's given by this formula. And it turns out that going the other way is basically the same except you incur a minus sign. Okay, and this is like a quantum state analog of the Fourier transform. If you're going to think of this probability, or not probability vector, the state vector as a signal, and you imagine taking that signal and actually applying the Fourier transform to that signal, the thing you'll get out is the same as is the signal that would be represented by this state. So it's really applying the Fourier transform on the signal represented by these quantum states. And we won't really actually need any of the formulas, but there are some useful features of the quantum Fourier transform. So one is that by applying it to ket 0, we actually get this kind of uniform state vector, this uniform superposition over all strings. So that's nice. We have some properties about subspaces that if I have, so imagine now I'm not just having one component, but I have several components and I apply the QFT to all of the components. My components actually form a vector space. And I could imagine what happens if I have like a superposition over a subspace. Well, it turns out that the quantum Fourier transform maps you to the if the superposition is uniform, so like all the amplitudes are 1 up to some normalization, it actually maps you to the uniform superposition over the orthogonal subspace. Okay, so this is just a property of Fourier transforms. There's also this fact that if you shift your input, so if you just add some offset to your state vector, and you apply the Fourier transform, adding that offset just now turns into a phase, a particular phase term. And it goes both ways. If you have a phase, then you get an offset. And then lastly, there's this convolution theorem. This isn't particularly relevant for anything I'm going to be talking about today, but is also another kind of important feature of the Fourier transform. Okay, so with that, let's actually see how we break things with quantum computing that we can't do classically. So kind of the most famous thing that quantum computers can do that classical computers can't is something that I'll call period finding, goes by other names. So here's the setup. So we're supposing we're given a function f, and we're not told anything about f, except that there's the following promise. There's some hidden subspace S. So f is f is gonna have multiple components to its input, 2 or 3 or whatnot. I mean, this all actually would make sense even if there was a single input, but it's kind of easier to think about, I think, in the high dimensional case. So there's some hidden subspace S such that if I take f of x, or I take f of x plus y, where y is any vector in S, any vector in my subspace, it doesn't change the value of f. They're the same thing. So on the subspace S, f is constant, and also on every coset of the subspace S, f is constant. Okay, so moving around by vectors in S doesn't change anything. On the other hand, if I move around by something not in S, then it does change the value. So on all these, on the subspace and everything parallel to the subspace, the function is constant, but then it is differing as I'm like going to different cosets. And your goal is to find S, right? No, nothing about dimension. I mean, ultimately the domain here has to be exponentially sized so that it's polynomial bit length or something. But yeah, the dimension could be, the way I've defined it, it doesn't really make sense necessarily for the dimension to be 1, but the dimension could be anything as long as the overall space is exponential sized. Okay. So there's an easy theorem that you can prove, I'll leave it as an exercise, that if you're a classical algorithm, and you're only making classical queries of this function, so you're treating it as a black box, you don't know anything about it, you're just gonna query it, and you're just making classical queries, that the best you can do is exponential. Because basically, you don't learn anything about S until you find two vectors that are actually in S. So if S is somewhat sparse, your chance in a polynomial time of finding two vectors in S is negligible. And you can, show that for appropriately sized subspaces S, that you actually will need exponential time. Okay. But it turns out quantum algorithms can actually solve this. And this was, a version of this was shown by Simon, and then more famously, Shor showed how to do this, and this was, how he ultimately showed how to factor integers and solve discrete log on a quantum computer. Okay, so how do we do this? I'm gonna drop normalization just because it's messy. So first you're gonna prepare this uniform superposition over x, comma 0. And remember, we can create the uniform superposition over x by applying the Fourier transform to 0. Basically, I start with 0, 0. I apply Fourier transform to the first one. Okay. Now I'm going to take, I'm going to assume query access to, remember this unitary O sub f that we defined? That maps x comma y to x comma y XOR f of x. Well, here y is 0, so I just get f of x here. Okay, so now I have the superposition over x comma f of x. All right. And next I measure f of x to obtain some y. And I didn't really talk about what happens when you do a partial measurement. But you're right, because I don't want to measure x yet. I only want to measure f of x. But basically what happens when you do a partial measurement, so if I only measure the second register here, I'll get some value y. And then the state collapses to have the y here, and then all the x's that were consistent with the y. So basically I just chop out, I have this, this whole quantum state, and I just chop out all the parts that were inconsistent with y, and whatever's left I renormalize. Remember, the norm always has to be 1, but I'm ignoring the norm anyway. So when I measure y here, the x's collapse to just the x's such that f of x equals y. Okay. So far I haven't actually done anything interesting with quantum. This is really no different yet, or so far, to just querying f on a random input. But now the interesting stuff happens. So I'm gonna just discard y. We don't actually care about the output of f. What we care about is this, the vector of x's. So the superposition of x such that f of x equals y. And now remember, the structure of f is such that it's constant exactly on the cosets of the subspace S. And so I can rewrite this as a superposition over x in the subspace, except I might have an offset, right? And this x0 is just any vector in, this should have not been S. X0 is any vector such that f of x equals y. Okay, so I have the superposition over the coset. Still can't directly do anything with this. If I measure this, I just get a random pre-image of y, which isn't particularly interesting. But now I use the QFT and this rule about cosets, about subspaces. So if I apply the QFT, if I first imagine that the x0 wasn't there, the rules of the QFT means if there's no x0, this is the uniform superposition over the subspace. QFT maps to uniform superposition over the orthogonal subspace. And the shift just picks up a phase. All right, so QFT maps to this state here. We don't actually care about the phase at all. That's what's really nice about this. And so now I just measure this thing. And I will, basically what I'll get is, so this is just a phase, its norm is 1. So all of the z's in here have the same squared amplitude. So when I measure this, I actually get the uniform sample from S_perp. So I measure z and get a random vector in S_perp. And now I just repeat this a few times, and I'll eventually get a spanning set for S_perp that tells me what S_perp is. And then once I know S_perp, I can just use linear algebra to find this. All right, and so that's basically it. That's period finding. And really, this is all the quantum algorithm I'm going to talk about today, because as I said, I want to get into the interesting stuff. Okay, so actually, before I go on, any questions? Okay, so now let's get to crypto. So for this morning, I'm only going to consider classical cryptosystems, but we're going to be worried about quantum attacks on them. In the afternoon, Dakshita will be talking about actual quantum models. So first, let's see what quantum computing means for our current existing cryptosystems. Well, it turns out that period finding actually allows you to solve a lot of the crypto we have today. So here's an easy one. So discrete log can easily be seen as an instance of period finding. So remember discrete log, I have some group, I don't care what it is as long as it's efficient. And I have a generator G and some, H equals G to the A, and my goal is to find A. So what I'm gonna do is I'm gonna define this function f of x comma y equals G to the x H to the y. And now it turns out that this function is periodic. Why? Well, if I add minus a comma 1 to my input, the minus a, goes in the exponent here on G, and the 1 goes on H, but remember H is G to the A, so they cancel each other out. So if I add minus a1 to x comma y, I don't change the value of f. And on the other hand, if I add anything that's not in the span of minus a comma 1, it will actually change the value. So my function f now is a valid instance of the period finding problem, where the subspace is defined by this minus a1 vector. So I just apply period finding, I get minus a1, and that just tells me A. Or technically I would get like a multiple of this, but I just divide them. And I just divide the two components and I get A. Okay? So if you have a period finding algorithm, in particular if you have a quantum computer, you can break discrete log. Okay, factoring you can actually also see as period finding. What I have on the slide here is a bit of a lie, but because there's a little more to it, but this is the gist. So, okay, we're gonna imagine we have a large composite that's the product of P and Q, and our goal is to find P and Q. We define this function f of x is G to the x mod n. I don't care what G is, it's just a random value mod n. And now observe that if I add a multiple of the totient of n to x, I get f of x. So exponentiating is just naturally periodic. So if I could find this period, if I could find this p minus 1, q minus 1, well, that actually tells me p and q because I can just, I have two equations on p and q, I just solve. Now, really, you actually have to work harder. This is a 1D case. I was kind of, when I defined period finding, I was kind of thinking multiple degrees. Here, you're really over the integers as opposed to, mod some finite value. So there's some extra work to actually get this to go. But this is there is a periodic function in there, and you can use it to break period finding.
Can you think of this just as a classic reduction from factor into discrete log, and then you do the quantum?
Yeah, I suppose. Okay. Okay. So what are the consequences? Well, all the widely used public key crypto systems today.
What was the question? I don't know the answer.
Because you'll run the discrete log, you'll always get the same x. You're not gonna get something outside, like x plus p minus 1, p minus 1 is like outside the. It's not clear to me that if you do discrete log, you'll ever get like the plus. You may always get this.
Yeah, I mean, if you define your if you define your domain to be much bigger than n, you do have to work a little harder also.
In the same way that the reduction between factor and discrete log, we have to work with. It's not an immediate reduction. Yeah, it says.
Yeah, you have to work a little harder. You have to kind of play around with the domain, make it bigger, so that when you solve discrete log, you're actually finding a collision. But in any case, this is a lie. You do have to work a little harder, but hopefully it gives you.
Either way, you'd still have to do it over the integers, so I don't think it would make anything easier to do the discrete log version.
Okay. Okay. So for the consequences, I'm going to roughly divide things into two buckets: public key cryptography and private key cryptography. So for public key cryptography, all of the widely used schemes today rely on factoring or discrete log. So they're all broken quantumly. On the other hand, for private key or symmetric key cryptography, there's no periodicity in them, so they at least seem immune to Shor's algorithm. Presumably, they're actually quantum secure. We do have to pay attention. There's another algorithm I didn't go over, which is called Grover's algorithm, which just gives you a generic quadratic speedup over classical brute force search. So a lot of symmetric key crypto is kind of dominated by our assumed hardness is dominated by classical brute force search. And so you have to pay attention to this quadratic speed up due to Grover, but you can usually just double your key size in your file. Okay. Okay, so this is what it means for current crypto. And now we'll start actually, what do we do going forward? We know some things are broken, some things maybe not. What does cryptography now look like in a post-quantum world? Okay, so modern cryptography, classical cryptography, is defined by the following formula, or at least this is how I think about it. So we insist on provable security. And what is a provable, what is a security proof? It's really not a proof in the mathematical sense, or maybe it is, depending on how you look at it, but basically a proof consists of three forms. So first we need a formal security model. We need to actually, know what we're proving about. So we have some model M representing classical attack. In the classical world, we would think about classical attacks, classical realizable attacks. So, existential unforgeability in CCA security, whatever, some formal model. Because we can't do anything unconditionally, we always need some assumption. So we're gonna have some computational assumption P. And this must be some realistic assumption. It doesn't make sense to your assumption to be 1 + 1 = 3. Some realistic assumption, like in the classical world, hardness of factoring or discrete log. And we actually have also, you can also imagine generic assumptions, just assume one-way functions, assume PKE, so forth. And then you have a proof that if your assumption holds, your scheme is secure. And this is formalized by a reduction showing that if you have an adversary that breaks M, then you can break P. Okay. So when we move to the quantum world, we actually have to revisit all three of these. So a proof of quantum security of some primitive, we need a post-quantum model that accurately reflects real quantum attacks. We need some assumption P that makes sense against quantum computers. And then we need a reduction that transforms a quantum algorithm for M into a quantum algorithm for P. Okay? And the thing I want to really drive home is that a post-quantum proof does not look like this. This is what I have now is bad. So if you have a classical model and a classical reduction, but you upgrade your underlying assumption to a post-quantum assumption, that is not a post-quantum proof. At least not without some justification why you can do this. So really, and if you want a post-quantum proof, you really need to make sure all three of these ingredients make sense.
I understand for the reduction, but for the model, you said that classical model is a subset of the quantum model. So can't you just think of the...
So classical algorithms are a subset of quantum algorithms. So you could imagine you take your classical model and you just say, oh, by the way, we're gonna replace PPT with QPT. We're gonna allow our adversary quantum polynomial time, but otherwise not change the model. And usually that works, but there will be cases, and we'll see them today, where this doesn't. Yes.
Why would you maybe not consider these things mathematical proofs?
Oh, I mean, they are in the sense that they're formal. At least we hope that they're completely formal. But we have, it's conditional, right? And then you could also debate what's the right model. So there's a little bit of potential subjectivity, but more or less it's a method. Okay. So let's get into the first part. So I'm going to talk about the assumptions, and I don't have nearly enough time to talk about all of the different post-quantum assumptions out there, so I'm just going to pick two. And I think they're the two that have gotten the most attention, but they're also my favorite two, so there's a little bias here. So let's start with something called a group action. So recall the classical Diffie-Hellman protocol. So in the classical Diffie-Hellman protocol, we have some group G. And how do Alice and Bob establish a key? Well, Alice chooses a random A, computes G to the A. Bob chooses a random B, computes G to the B. And then they send their G to the A and G to the B to each other. They keep A and B private. And then they compute the shared key, G to the AB. And they can each do it. Alice takes Bob's message, raises it to her secret value. Bob takes Alice's message and raises it to his secret value. Okay, so an observation about this protocol is that in some sense, we don't need the full structure of a group. We only need exponentiation here. Nowhere did I kind of explicitly multiply two group elements together. I mean, the way we implement exponentiation is through multiplication. But if you kind of abstracted away exponentiation as a monolithic operation, all we need is exponentiation here. We don't need group multiplication. So Broussard and Young in 1990 proposed, not for Diffie-Hellman, but more for understanding commitment schemes, but they proposed the notion of, I mean, group actions are a concept from math, but they proposed thinking about group actions in the context of cryptography. And basically what a group action is a group where you can exponentiate, but you can't multiply. And a little more formally, so it's a little confusing because I'm gonna change the roles of what a group is. So in a group action, we have a group G acting on a set X. But when we're trying to think about it in terms of groups, like what was formerly a group is now X. And now we have this other thing that's a group, which is really like ZP star. But anyway, we have this group acting on X through some binary operations. That means it takes as input a group element, a set element, and outputs another set element. And the key identity we have is that basically this star operation, this group action, respects the group structure. So if I take A times B and act on X, that's the same as taking B, act on X, take the resulting set element, and then act on it with A. Okay? So exponentiation, group exponentiation is a group action where the group is ZP star. So, this G is, down here it's G prime. The group acting on the set is GP star, ZP star, where P is the order of the group. I'm assuming a cyclic group. And the set is, the group elements of the original group. Okay? And here's maybe this will make it more clear. So if I have a group action, I can also carry out Diffie-Hellman. Alice and Bob will choose random group elements now. And they will act on, there will be some fixed starting element in the group action, and they'll just each act on that set element, send over A star X and B star X, and then they can compute the shared key as AB star X, and they use the fact that the group is abelian and that the star respects the group action to get the same key. And this is really this is exactly an abstraction of the original Diffie-Hellman, just working in the language of group actions. And just like Diffie-Hellman made sense in group actions, a lot of the assumptions we make on groups have natural group action analogs. Discrete log is given two set elements with some group element that goes between them, recover that group element. Here I'm going to assume, I'll always assume that that there's kind of a unique G, that is an assumption, but many group actions satisfy that. CDH is if I'm given A star X and B star X, compute AB star X, and DDH is the analogous. So these are literally just taking discrete log CDH and DDH and just, just translating them to the group action language. Okay, so why do we care about group actions in a quantum world? This was first, I think, observed by Kubanis and Rostovstev and Stulbunov. I'm sure I butchered that. And basically, the observation is if we look at the discrete log algorithm, which is just this period finding algorithm for this function f, well, look at f. F requires computing g to the x times h to the y. There's a group multiplication here that's not easily abstracted away as an exponentiation, which means that this f function we can't compute efficiently. And if we can't compute this f efficiently, then maybe we can't actually solve discrete log. Maybe we can't if we can't compute f efficiently, we can't period find on f. And maybe that means we can't solve discrete log.
Yeah. There are too many groups here. So everything is a group. So what exactly is not a group?
So here I'm So here I'm going back and forth between like the group version and the group action version. So here I'm thinking of just this should really be like G star X, or sorry, X star G, okay, fine, I've switched G and X here. But the point is like in the discrete log attack, right? Think back to the discrete log attack. Forget that I told you anything about group actions. This is the syntax for the original discrete log attack. To compute this function f, I need to take g to the x, h to the y, and then I need to multiply them together. And I said let's abstract out exponentiation as a separate operation. So I can do this with exponentiation. I can do this with exponentiation, but I can't take the product just given the ability to compute exponents.
But what do you mean, when you say a group action that is not a group? A group action. So
What I mean a group action that wasn't just group exponentiation. So group exponentiation is a particular kind of group action, but for that group action, you can actually compute. There's a notion of a product here.
So basically, what you want a group where you can efficiently exponentiate, but not efficiently multiply.
Yeah.
Right. Because then you don't have this algorithm, and then the hope is discrete log is
They're going, okay.
Yeah. Yeah. So based on this, so on a group action, you can think how I solve it. You can try to port over Shor's algorithm for discrete log, and you'll see it doesn't work. And the intuition for why it doesn't work is because discrete log require the ability to multiply group elements. We only have the ability, intuitively, we only have the ability to exponentiate. And so this gives some hope that maybe group actions are post-quantum. All right. So in terms of okay, but any particular group action might actually there might actually be a group structure underlying the group action, which we can apply Shor's algorithm, solve discrete log. So we need some group where intuitively exponentiation is easy, but multiplication is hard. And we don't have a lot of candidates for that, but we have some. So the most famous one, and the one that's gotten the most attention from cryptographers, are isogenies over elliptic curves. I won't define what those are. Sort of something from number theory. And what's nice about these and why these have gotten a lot of attention in the crypto landscape is because they're Abelian. And if you think about Diffie-Hellman, you need it to be Abelian in order to get the protocol to work. And there are actually, there's a richer set of non-Abelian ones. These haven't gotten a ton of attention from cryptographers, some. Maybe the most famous is Michaelis. It's usually not described as a group action, and it requires more structure than the group action structure. But there is a group action, a non-Abelian group action kind of hiding inside Michaelis. And there's actually been, there are other proposals for post-quantum cryptography that can be reasonably abstracted as group actions, but most of them are not Abelian.
So you seem to, there's some things you want and some things you don't want.
Yeah.
Right? And you've sort of kind of boxed yourself in to how cryptography used to work for the ones, the things you want.
Mm-hmm.
And you say, but there's some things I don't want because that helps attack.
Yeah.
It's very curated,
Yeah, but I think what I like about group actions is that we can draw on a lot of intuition that we developed over the decades from thinking about groups. But yeah, we have to throw some things away because now that we don't have multiplication, there are some things we can't do. So some things we have to throw away, some things we have to reinvent. But I think we can develop a lot of intuition, or take advantage of a lot of intuition to do interesting crypto.
When you say abelian and non-abelian, is it the underlying group that's?
Yeah, the group G acting on the set. So in Michaelis, the group is basically the symmetric group is acting on a particular set. And because things are when you're non-abelian, like it's not obvious how to do Diffie-Hellman. So Michaelis, you can do public key crypto, but it's a completely different mechanism than the Diffie-Hellman protocol. So you're kind of, you usually actually just ignore the fact that there's a group action here, but there is a group action, and the hardness of Michaelis is basically the hardness of discrete log.
So earlier you said you want group actions that are not themselves groups. How does that?
Well, so so I mean, a group action has a group in it, but I'm not relying on the discrete log of that group. So when I say a group action that is not a group, I mean a group action where my set is not a group, and the group acting on it is not the exponent. Yeah.
So code in basically codes are kind of related to lattices. So the question is, where would you place lattices? And what about other coding constructions? For example, LPN, Alekhnovich public key. That looks like discrete log, the Diffie-Hellman.
There's a way to get there's a way to get like kind of approximate notions of group actions out there, but they're not the clean version.
So McLeese is cleaner than the lattice-based?
Yeah, but again, like you actually are throwing, you don't actually care that it's a group action for, the protocol. But there is a group action in there because if you, for those of you who know McLeese, basically you're taking the, this matrix and you're permuting, you just permute the columns, right? So you have the permutation group acting on this matrix by permuting the columns. And then you do this other operation to kind of scramble the rows as well. But you can think of, that gives rise to a group action. But because it's not abelian, it doesn't immediately give you Diffie-Hellman. You have to, you exploit the fact that this matrix relates to coding problems, stuff like that.
For McLeese, you don't know all the worst case to average reductions and so forth, do you?
Not that I know of.
So all the properties that have been developed over time.
So in group actions, the worst case to average case reductions are also different. Like if you think about the worst case to average case reduction for DDH, it doesn't work on a group action. And actually you have to work a lot harder to get a reduction.
I'm talking about the lattice ones.
Oh, okay. Yeah. Again, maybe I shouldn't have put McLeese here, but I just wanted to say that like people have studied things that have a group action in them in the post-quantum setting, but it's not a.
So just to clarify, you're saying McLeese, the transformation from secret key to public key could be viewed as a group object.
Yes.
But McLeese encryption is not an application of.
It's not like it's not like Diffie-Hellman over that group action. It's completely different.
And that would that be insecure if you kind of take
Well, it wouldn't be correct because you're not a abelian. So if you're
I just want to clarify. So you're saying in these group action assumptions, the X not only does not have to be a group, but you expect the set X to strictly not be a group?
Yeah, basically we don't want any structure on the set except the fact that there's this action, this other group action.
So it seems to me these are candidates because we don't know a way. It seems hard to find a way to reduce the problem to period finding.
Yes.
Is there any efforts on trying to formalize this or?
Black box on that particular question, on if you can show a formal relation to period finding, I don't know. Let me actually talk about the quantum hardness, and then we'll probably have to take a break. But so the hardness of these things is purely conjectured, and it's actually a little unsettling, the current status of things. So first is that there's this old result that shows that you actually can break any group action, even a non-abelian one, like any group action I give you, you can actually break it by making only, this should have been polylog, sorry for the typo, making polylog queries to the group action. And polylog is, we're thinking of the group as exponential size. The polylog is just polynomial. So in a polynomial number of queries to the group action, you can actually solve discrete log, and that would break all group action-based crypto. The caveat is that there's computation time outside of the queries to the group action that runs in exponential time. And this is very different than what we, and this is for any group action. It's totally generic. You don't need any structure of the group action. And this is very different than the classical group setting, because in classical groups, we actually know generically you can't do better than exponential time. Here, generically, basically you can't get the query lower bound, and you still need to make some additional computational assumption. And it gets worse. So, we usually want abelian because that helps us do things like Diffie-Hellman. And for the abelian case, there's actually a sub-exponential time attack to the Cooper-Berg.
Do you have some generic group model for quantum attacks that shows it?
Yeah. So it's not hard to define a quantum generic group action model, and in that model, these algorithms. So what does this mean? It means that there is some underlying, because of this attack, there's some underlying actual computational hardness that we have to assume is true. We can't just, you know, like reason about generic attacks like we did in the classical world. And then because of the sub-exponential time attack due to Kuperberg, for theoreticians, it's not such a big deal. Other than maybe the existence of a sub-exponential attack makes you worry that there's actually a polynomial time attack. But in practice, this is actually bad news because it means that you need to set your key sizes to be rather large to avoid this attack. Yeah.
Do you imagine it would be okay for X to be a ring?
I don't know. You know, any structure that you add, you're running the risk of introducing new algorithms. Okay, so I know we started a little late, but it's time. Should we break now, or should I like finish up group actions?
Yeah, I
or-
would do it, you decide whenever it makes no sense.
Okay, so let's spend a couple more minutes. Okay, so with group actions, as was already pointed out, there's a problem. So we avoided Shor's algorithm. We hope that means there's quantum security. But the fact that we have a lack of structure means that a lot of our applications are now in trouble. Not from a security perspective, but just from a functionality perspective. And take the example of signatures from groups. I don't know if this was technically Schnorr or, you know, Schnorr some variant of this, but whatever, it's close enough. So how do I sign a message? So my secret key is going to be an exponent. My public key is g to that exponent. I'm going to create a new random group element just by raising g to the s. I hash it together with a message to get a challenge. And then I output this R, which is, you know, a linear combination of my global secret key and my kind of ephemeral secret here, and the linear combination is determined by the challenge C. So this is just taking you know, the Schnorr identification protocol and collapsing it using Fiat-Shamir. I don't even care about security at the moment. I'm like, this is just about correctness, this discussion. Okay, and now verification, you can easily verify. Usually you would actually only give out 2 of these 3 values, but whatever, it doesn't matter. So you check that the challenge was actually computed correctly, and then you check this equation here, and you can verify that if I honestly computed the signature, that this equation will hold. But notice, I have this pesky group multiplication here, and it's not obvious how to carry out this check with just group exponentiations. Okay, so what do we do if we're going to try to translate this to a group action signature? We're a little bit stuck. It turns out there is something you can do, but it's very unsatisfying. So how do I sign? It looks somewhat similar to Schnorr, and it's certainly inspired by Schnorr. So my secret key is again going to be, well, now it's a group element, but it's, you know, in group actions, think of the group element as like the exponent. I compute a random set element by acting by another random element. I hash it down using Fiat-Shamir, but now my challenge is just a bit. It's no longer you know, this big thing. It's going to just be a bit, and this will be important to actually get correctness. Okay, and then the last component, this is basically the analog of what we did in Schnorr, just expressed in group language, and with, you know, the C from before replaced by B. But the difference is, like, remember on the previous slide, this uses the full fact that the exponents of a group are, you know, ZP, it's a ring. I can multiply and I can add in the exponent. In a group action, so this is you know, this is the stand-in for the exponent, but now it's just a group. There's no ring structure. But I can still, you know, by basically using B as a selector, you know, select between, you know, identity or not identity, I can still you know, kind of do something that looks like the ring operation. Right, and then what do? I check, you know, I first check that B was computed correctly, and now I check these expressions, and you can check that they're right. And I can, you know, I like kind of abusing notation. I can write this a little more concisely like this, where, you know, basically if I have something to the 0, I just erase it. And if I take this convention that something to 0, I just erase, this sort of kind of looks like the verification in Schnorr, but now it's actually an operation that I can compute even though I have this more limited structure of the group action. Okay, but there's an obvious problem that because my challenge space is only a single bit, I can actually forge signatures trivially. Just, I can just try some random values and it's probability half. Oh, this should be a here.
Are you
Yeah.
showing a signature scheme that works? Or is it
Yeah,
not?
well, not yet, not yet. This is broken because the challenge space is
Even
too
if
small.
you are fine. Think of it as an interactive.
Yeah.
No, Fiat Shamir.
Yeah, so you can boost sound. So the protocol I described doesn't work because it's not sound, but I can, do parallel repetition or something to amplify the soundness. And you can do some optimizations and show that this blows up the signature size by lambda. You can get a little better, and we actually showed among some class of natural schemes that this is optimal. But this means that there's a cost to move into group actions, that you're really blowing up your signature size. So like Schnorr signatures, from a practical perspective, Schnorr signatures are very efficient, right? They're, I don't know, 512 bits or something. But now they're much bigger. We basically blew things up by security parameters. And so this is unfortunate. I'll note that there is a construction of signatures using isogenies over elliptic curves that gets a much better signature length than what you would get from here. But it kind of uses more structure of the isogenies and it departs from the group action abstraction. Okay, I think maybe we'll stop here and then I'll very briefly talk about lattices and get on to the new
Can I
stuff.
just ask something?
Yeah.
There's several axes according to which you have thought. One is that you want to have an assumption which is not big.
Yeah.
Two is you want to have efficiency and you have or whoever designed these schemes, had some very clear goals in mind.
Mhm.
So I'm not sure how to evaluate this, Because when you're talking about size and you're talking factor of 2, how's that really, are we talking theory or are we talking practice?
I mean, we should be talking to each other, right? The theory motivates the
No.
practice and vice versa.
It's kind of early to talk to each other because, we don't even know which assumptions hold.
That is true, but we're also like, NIST had their standardization process, so in some sense we're late, right?
So we are doomed. Yeah.
I don't know. I think we need to be talking about these things now because the process takes a very long time, and if you're an optimist, you might, or if you believe
Yeah,
what
but if
companies say, quantum computers are coming.
But if you zoom into factor of 2, it's going to be very hard to make progress.
Yeah, well, okay. I'm not talking about factor of 2 here. I'm talking about factor of now.
No, but
So-
I think the point is, I think what Mark is saying, he's saying, look, let's talk about fundamentals, forget about and then sprinkles on top, by the way. So I think at least what I see the style of this lecture was actually about not
Up to this point.
the factor of 2 is just by the way. It's not like, that's not the essence. It's more about.
No, I agree with everything, but up to here,
I don't know, but there's a very interesting theory question here, right? Can you get signatures from group actions that only use a constant number of group elements? Like that's a theory question.
Yeah, that's clear.
Yeah. So, it's certainly very well motivated by practice. The length of signatures has been a kind of a sticking point on the attempts to get post-quantum signatures, but it also, I think it's a very interesting theory question.
Okay, so thank you, and we'll take a break. We'll come back.
Everything else gets wrong, then is something. Gets wrong.
No,